Welcome to this public seminar. My name is Obed Mugaka. I'm from the Department of Electronics and Communication Engineering. So my seminar, my research is about an FPGA-based deep learning accelerator for image processing applications. And this was the main objective or the main title for my research. I was under the supervision of Professor Mohammed Said and Dr. Rami Zawail, as well as Professor Koji In. So this presentation is outlined as follows. I will introduce this work, uh, basically the introduction to deep learning that I will be using. I will conduct some literature review about about the major techniques I will be using in this work. I also now talk about my two major works, that is the development of tiny emergency net, a lightweight model for aerial image classification. I will talk about tiny emergency net as well as its FPGA implementation, as well as I will finish with the summary of the contributions and future works. So deep learning has found applications in many areas and domains, ranging from robotics, computer vision, finance, agriculture, entertainment, healthcare, and very many others. And it also includes has been used in remote sensing. This is because deep learning has proven to be efficient in image classification, image detection, object detection, image segmentation, and other applications. So our focus in this work will be in remote sensing, and in remote sensing itself, there are several other applications or subdomains. It has been used in forestry, in agriculture, in power lines and towers and accessories, and also in artificial facilities as well as nature environment. And particularly in remote sensing, there are various techniques. There could be satellites, uh, platforms, high aerial platforms like drones and high altitude helicopters. But also of interest is the unmanned aerial vehicles that I will focus in this presentation because of their nature or their advantages towards remote sensing in the particular application. For example, in the last subdomain, they are used in emergency response. And in emergency response, this involves natural or anthropogenic disasters. This includes earthquakes, fires, they could be forest fires or normal fires, traffic accidents and floods, and many other scenarios. And in such an application, we get response teams experiencing various challenges. These include they need to make swift and time-sensitive decisions so as to save lives, minimize damages, and coordinate rescue efforts. And in this particular application, UAVs are very key, and this is because they can carry specific image sensors for particular applications. They allow dynamic control flight planning as well as revisit times. They have controlled heights, and also that affects the resolution of the imaging. So this is why they are very key in this particular application in emergency response. However, they have three major challenges, and this includes their limitation in battery lives, the battery or power capacity. They have limitation in terms of the memory they have on board, as well as the computing power they have on board. So it's very challenging to, the challenge here is that also, because we've discussed about the importance of deep learning in this application, the deep learning models are very challenging in terms of memory efficiency. In figure 1.4, you can see that these are actually well-known CNN or deep learning models and how they perform versus their computation demands. You see, for instance, in VGG19 that performs well in accuracy, it has an accuracy, top one accuracy of above 75, but it requires 150, around 40 giga operations per second. This is the computing demand of this model, for example. Not only the computing demands, they also have power energy demands. And figure 0.145 actually tries to illustrate the demands in terms of energy requirements for particular operations. So when you analyze this table or this figure, you will realize that actually the bottleneck or what predominates the energy consumption in this application is the reading of memory of data from external memory. And we have seen that these deep learning models have a number of parameters. So they require high computing intensity, as well as they have high number of parameters. So their memory is huge. So these are the challenges we have. So we have formulated our problem as follows. We acknowledge that indeed deep learning models are very crucial for this kind of application. However, when in applications where we have resource constraint devices, where we have low memory and lower computing and power capacities, so this is a challenge. And so our objective is to propose and evaluate various techniques to streamline these models, optimize them for efficient inference on resource constrained platforms. And in this case, an example of the UAVs. And then we present a high level approach of implementing this of a domain specific FPGA-based acceleration using a framework that we will discuss. So because this challenge has been identified, various works have been conducted to address it, and there have been proposed lightweight models for deep learning. And in this case, lightweight means that they consume less power. They try to make them smaller in terms of memory and also less compute intensive. So an example of this include mobile nets, SqueezeNet, Exception, ShuffleNet, EfficientNet. These are actually pretty common and state-of-the-art models that have been proposed. And when you look at them versus what we saw earlier in the graph in figure 1.1, is that they have been able to reduce the number of parameters from in the range of 20s of millions of parameters to less than 5 million parameters. But again, they have tried to maintain the accuracy. When you look at the top one accuracy, they're still in the range of 70s. And this is evaluated on a data set, the ImageNet data set that is pretty common in these applications. So one thing you will realize that they commonly use the depth-wise separable convolution. So this is lightweight model, the lightweight way of implementation of the convolution that takes less computing intensity. So because of this, the nature of this convolution, I've discussed it here. So in a standard convolution, if we took the number of operations as the complexity of this convolution, we compare with the depth-wise separable convolution, it will be shown as in these equations that, so what normally happens in the depth-wise separable convolution is that it's divided into two operations. One, we do channel-wise computation as in the second figure, and then we perform point-wise convolutions. Point-wise convolution, that means you have only a kernel that has one dimension, like one value in a certain dimension as indicated in the figure. So this convolution therefore has been able to reduce the compute intensity of convolution, so which we will leverage in this work to make the performance efficient. So another work that we consider is emergency-net. So some researchers proposed an CNN model that they called emergency-net, which was specifically designed for efficient aerial image classification. And they proposed a technique or an architecture they call multi-resolution atlas convolution feature fusion blocks, where they combined, they used atlas convolution. In this case, an atlas convolution is a normal convolution, but they expand it with a certain dilation rate. So they insert holes or zeros, or they skip the computation in such a manner. And the benefit of this is that it manages to enlarge the field of view. And this is why they are calling it multi-resolution. The importance of enlarging the field of view is to be able to perform what is called enlarged context assimilation. So this is important. However, the good thing with this dilation is that it does not increase any number of parameters, and it does not increase the computation. It's simply like using the same kernel but in a different way. So they proposed the use of 3 dilation factors, 1, 2, and 3, and they were able to achieve a 95% accuracy with only 90,000 parameters on a data set that we also going to discuss for aerial image classification. So with this advancement, of course, they have been able to reduce the computation and complexity of these DNN models. However, there's still room to improve them further because we are talking about UAVs that are resource constrained. So we continue on this work to enhance it using other optimization techniques. And some of those include quantization. So quantization actually aims at decreasing the number of bits used to represent the weights and activations in the models. And this leads to increased inference, reduced inference time, as well as reduced energy consumption. So there are 2 schemes of quantization. One, there is uniform quantization that has been adopted largely in implementation, and also there is non-uniform quantization. So uniform quantization has been able to perform well up to 8 bits. So where they reduce, normally the deep learning models are trained in 32 bits. So uniform quantization has been able to reduce the bits to 8 bits using uniform quantization with good performance. However, it's been noted that the distribution of weights in a model is not uniform. So you find that some weights are concentrated in a particular range of numbers. And so when you apply uniform quantization to this kind of distribution of weights, you suffer high quantization errors. And so this is particularly a challenge when now you move lower than a certain number of bits. And in this case, we want to move lower than 8 bits that have been used in uniform quantization. And so we propose to use non-uniform quantization in this technique. And it has also been proposed in literature. This is where they represent the weights in a logarithmic distribution. So use powers of 2. It's now called powers of 2 quantization to represent the number of to represent the weights and activation in the weights in the deep learning model. So the other importance, the advantage of using this, apart from reducing the size of the models as well as the reducing the quantization errors, the other advantage is that in powers of 2, the multiplication is no longer It's actually in hardware we now use bit shifting rather than performing the multiplication using a digital signal processor. So shifting is actually more efficient in terms of energy consumption. So this is the importance of this. However, with the powers of 2, there is also a challenge in that when you add or increase the number of bits to represent weights, there's a challenge that comes up that you are only increasing the resolution to the mean. So it means if you had a representation that uses 3 bits, you increase to 4 bits, you are not gaining from increasing to 4 bits because the resolution of your quantization is centered to the mean. So this is a challenge. So another scheme of non-uniform quantization has been proposed to solve this challenge that they call rigid resolution. It's now the new technique is called additive powers of 2. So rather than expressing the weights in powers of 2, we will express the weights in summations or additions of powers of 2. And this is the technique that we have proposed to apply in EmergencyNet to come up or derive a more streamlined model. So apart from quantization, there is network pruning. So pruning is actually a way of taking away redundant or of a parameterized models so as to reduce its size. Again, remember we are trying to minimize the size and therefore accelerate the inference. So when we talk about pruning, there are 3 questions. Is what are we going to prune, how are we going to prune, and when are we going to prune? So based on the granularities of pruning, we could prune in channel-wise, kernel-wise, vector-wise, or go even in a fine-grained pruning. And all these have various challenges because when you prune, you are introducing sparsity or like for example, when you prune in a fine grained, so it will have to be compensated in the computation or in hardware on how to do the multiplication. So we will discuss this, but the more favorite, okay, the more easier way of the one that is more easy to implement in hardware is one that is of a regular pattern, so that you do not have to compensate for irregularities in computation. And other works have tried to analyze various techniques on how to prune. For example, there are some work that take like what is the effect of removing some weight on the losses, and there are many techniques. But a recent work has also proven that there is other works that in terms of how to prune, there's pruning that can be done while you're training the model or pruning after training the model. So, but it has been shown that once you have a lightweight model in the first place, pruning after training is as good as pruning while training. So you do the pruning and then do the training and then prune and then retrain to see the effect of this. So this is what we will also adopt. Now, apart from the software or the model optimization, there comes to the hardware implementation itself. So for acceleration of these kind of models, it is noted that CNN structures actually possess a certain characteristic that is very nice for acceleration. They are highly parallel. It involves like doing a lot of many loops of computation, which can be conducted in parallel, also applied in a certain pipeline. So there are various platforms for acceleration. There are CPUs, there are GPUs, there are FPGAs, and also ASICs. These are application-specific integrated circuits. So when you look at them, FPGAs are highly flexible as well as they are very efficient in terms of energy on the amount of power they consume. And because they are customizable, they are therefore smaller in size when you map your deep learning models to them. And also you can customize memory, unlike CPUs that where you have to buy an external memory. So in this application, we have chosen to use the FPGAs because of these advantages. So FPGAs provide us with the flexibility, as we said earlier. So we are able to employ certain optimization techniques. These include to be able to reuse data rather than, remember in the beginning we said one of the challenges in computation is that access of external memory is high energy costly. So to reuse data that we get into the FPGA, to do pipelining so as to improve latency, like to get results faster, and also because we said a convolution is highly parallel, it has so many loops, so you can perform certain loop rearrangements and unrolling, and also tiling certain operations together so as to increase efficiency. So also there are three major kinds of FPGA accelerators. There are accelerators that are specific to a particular application. There are accelerators that are been designed for a particular algorithm, and also there are accelerator frameworks. And in this case, they are like templates of an accelerator that you can configure or tuned to a certain application. And this is what we have chosen in this work. So we will take a framework that is giving us the opportunity to customize. And this is especially important for example, domain experts, people who are coming from not in the digital design. So you get a template of an accelerator. Now your work will be to do what we call design space exploration. So we study how to configure it to get more efficiency. So this is our first work that we performed. So we took emergency net that we have already described. We did optimization using channel-wise pruning and additive powers of quantization. And then we were constrained by power, memory, and the intensity of computation. And so we finally got tiny emergency net. So this will be the description of the work that we did. So for the evaluation of this work, we use this data set. It's Aerial Image Disaster Event Recognition data set that I will be referring as AIDA. It has 5 classes. There are many disasters, but we considered 5. Okay, 4 with a normal class. There's collapsed building, fires, floods, and traffic accidents. So we split this data set into the training, validation, as well as the test sets. Okay, one thing we realized with this kind of application and why it was important to apply the multi-resolution is that we have limitation of, we have less real data, because these are not events that occur every day. So sometimes you get images on a certain event more than the others. So the data set is imbalanced because you see some classes have fewer number of images, and to compensate for this, we did what we call class weighting. So you give more weight to a certain class so as to compensate for its lesser number of images. So the first thing we performed on the emergency date is channel-wise pruning. And remember, we said depending on the granularity of pruning, we will get a more efficient implementation on hardware. So we did channel-wise pruning, and the pipeline we took is that we first trained the emergency net from scratch to evaluate its performance, and then we set a predefined uniform reduction ratio. In this case, because we were reducing the number of channels in the architecture of the model, so we were removing a certain number of channels per layer, and then that is determined by the reduction ratio. After this, we retrain the reduced network and to see its performance, and then we repeat until we now have a trade-off between the size as well as the performance. So another important thing to notice that channel-wise pruning is such that when you prune certain number of channels in the initial layer, it will affect the next layer in that it will reduce the filters in the next layer. And so it has like a ripple effect. So you reduce certain number of channels, it reduces next layers. And when we analyze the effect of increasing the reduction ratio in figure 3.5, we were, with increase in the reduction ratio, we were losing the accuracy. And so this is where we had to perform the trade-off. Now, as we reduce the model, how much are we losing in accuracy? And as per this case, with 0.6, it was quite of a balance between reduction in accuracy versus the size. And so this will be the point at which we continue working on. So after pruning, we then performed the additive powers of quantization that I mentioned earlier. So to describe this technique that we use, we can consider quantization as a two-process or a two-step process. One, we first clip the weight into a given range, because we will also talk about in deep neural networks, the range of weights is really large. So you have to clip the weights to a certain range, and then after you clip them, you project it into the quantization level. And we said that in additive powers of 2, the quantization levels, which are described by equation 3.2, are in terms of sums of powers of 2. And we also described that the importance of these sums of powers of 2 is that as we increase the number of bits to represent the weights, we are not having the rigid resolution. And so we are retaining accuracy as much as possible. And so in this case, we majorly use these two equations in 3.1 and 3.2 for the representation of weights. So in our experiments, we test three bit widths. So we use 3, 4, and 5 as the bits to represent weights and activations. So, and also because we are talking about sums of 2, we tested with 2 as the number of terms in the powers of 2. So we say additive powers of 2, they could be 2 terms, 2, 3, 4, 5 terms, but we tested with 2 number of these terms. So as we also mentioned, that the importance of this is that we are doing now, rather than a multiplication, we will be doing bit shifting in the multiplication operation. So when you compare with the powers of 2, the additive powers of 2 and uniform quantization, we notice that this accelerates our computation. So in the doing of this quantization, we performed quantization aware training. This is where as you train, you are taking into effect the danger of quantization, because we said when you quantize, you are actually experiencing some quantization losses. So we want to minimize this by doing it in a quantization aware training. We adopted a technique that is called the reparameterized clipping function, that as much as we were clipping the weights, during training we consider them in the calculation of the gradient during training. So when you are actually doing the training of models, you are in the back propagation, there is the calculation of the gradient. So rather than doing the clipping without considering the weights that we clipped off, we include them in the training. And the other issue that we try to address is that the range of weights vary from one layer to another. You find that in layer 1 of the model, the weights vary differently than the next layer. So maybe if layer 1 has -5 to 5, layer 2 has -2 to +2. So those varying ranges were compensated by what we call weight normalization. So where you take statistics of all the weights and then try to normalize them so that you do not have a clipping threshold that is varying from one layer to another. So this is what we did. It's normal, it's just a simple normalization using the standard and mean deviations. So we did this normalization before the quantization. So this is the results of the full precision. This is before we do quantization. Full precision is that the model is in 32 bits. So emergency net previously that we adopted had this memory size with 95.7. After the pruning, remember we mentioned that we did the at various pruning ratios, but I did emphasize that we took 0.7 as the taken pruning ratio. And so at that pruning ratio, we got an F1 score of 94. So that's a drop by 1%, but we actually reduced the parameters by half, almost half. And we also compared with other models, which are, when you look at the data, they are very compute intensive as well as they are big in memory. So we therefore been able to achieve some reduction in memory size. Okay, so after this, we compare the result that we got from quantization aware training using the additive powers of quantization. So then we tested with 5 bits, 4 bits, and 3 bits. I have highlighted 4 as the most efficient in this case. We achieved a percentage F1 score of 93.6. Remember the original model had 95, so we have lost on accuracy a bit, but now you can notice that we have a smaller size with fewer number of. Now we have a model actually of 25 kilobytes. Remember we had the original model at 0.36 megabytes. So we have 25 kilobytes with only a reduction in 1% of the accuracy. And so the other achievement we got from this is that now rather than having a fixed floating point operation in the multiplication, floating point means that we have this number with so many floating point, like so many decimal points, or that's the float in computation. In this case, we are trying to use bit shifting, and therefore we have come up with, we used this metric, which we call fixed operations. So we take, if we have 8 bits, multiplied with another 8 bits, those are 64 binary operation, and then we divide by the APOTA number of terms we used, and then we come with, we get the fixed operations, which is more energy efficient as we earlier saw in the analysis earlier. So this is finally the model that we now call tiny emergency net. Is only 25 kilobits, and we have bitwise operations rather than multiplication, and it's only a loss of less than 1% loss in F1 score. So to this end of this part of the work, we have been able to integrate channel-wise pruning with additive powers of 2 to get this implementation that is far more efficient in terms of memory, in terms of computing intensity, and while we are preserving accuracy. So after this, we okay.
Don't forget we have another scenario at 11.
Yes.
And just have 10 minutes if you want to question.
Yes, yes. Yeah, so in the implementation part, so we took the same model. We were using a framework, and in this case, we adopted a framework that is available in MATLAB that gives us the opportunity to configure the optimization parameters. And so again, because memory is the key challenge, this tool enables us to configure how we read memory. Already we have discussed on how to streamline the model by quantization and pruning. So we had two key parameters, is that we are able to compute certain convolutions in parallel. And so when you set a certain number of parallel convolutions, you have to also configure the way you read the memory from data, from the memory, from external, the data from memory. So we were using, we used two models to test this, the deep learning processor. One is the mobile net that is common, and emergency net that we were considering. So we had to modify emergency net because it had some unsupported parameters or supported features. So we kind of actually did some pruning to it, so we get that more simpler architecture. And so when you normally have to do this, you lose some accuracy, because we lost from 95 to 93 because of this kind of pruning. However, we were able to accelerate it, and we will also actually see another from the mobile net that I get a performance of 20 frames per second. These are the frames you process per second, and the modified emergency net was processed at 74 frames per second. So this is the proposed design space explorations, how we tweak these operations or the configuration of this model, of this processor rather, to fit into the FPGA. So we did in a systematic way, changing the number of parallel computations in the hardware, and observing how it performs in terms of memory as well as speed. So this was the setup that we did. So from this setup, we compare before the setup and after the setup. We can see that in FPGA there are three resources: the lookup tables, there are BRAMs, which are like memories, and also digital signal processors that perform the multiplications. So when we compare before and after, we see that after we did the design space exploration, we were able to increase the inference from, for in the case of a mobile emergency net, from 26 frames per second to 74 frames per second. This is really good for the application in emergency response, because we need swift and time sensitive decision making. And the thing is that we reduce the number of resources we use from, for example, 80% utilization of the FPGA to less than 50% of the FPGA. And so this concludes our work. And in summary, our contribution is that we proposed a co-design uh, optimization approach for especially UAV-based remote sensing in emergency response. And we applied on channel-wise pruning coupled with additive power of 2 to streamline the emergency net and get a smaller, tiny emergency net. And then we proposed a systematic optimization for FPGA implementation using MATLAB's deep learning processor. And we have some future work is actually to now, remember we said the APOT implements speed shifting, which we propose to develop a kernel that is more specific for this kind of operation. And then this will be our future work. So thank you. And I don't have any questions.
Any questions? It's very clear.